Okay. So, we have already talked about single sideband modulation, right, in the last class. So, what we wish to do now, we have already told that the single sideband modulation, we have already seen the frequency domain representation, and through Hilbert transform we could finally get that the SSB signal, if it is upper sideband, it looks like this, MT cos omega ct minus MHT sin omega ct. Take that as a homework. If we just do the lower sideband, this will just become plus, nothing else. Okay, so this can be proven. So either upper sideband or lower sideband, it's just this separation of this plus sign or minus sign. Okay, so let's say we are just taking this. So that means the generation is pretty easy. You take this MT, okay, take into two arms, okay, and then here you give this Hilbert transform, which is minus pi by 2 phase shifter. Okay. Remember this minus pi by 2 phase shifter for each frequency component. We have already have one understanding of that. So you take that, and then here you generate a cos omega ct, directly put it over here, multiply it. So that will generate MT into cos omega ct, that you take in one arm. Here you give some pi by 2 phase shift, okay, that will generate cos omega ct, sorry, from cos omega ct sin omega ct, and then you multiply. So this will generate MHT into sin omega ct. So here you will get MHT sin omega ct, and here you will get MT cos omega ct. So if you wish to do upper sideband, you just add with this plus this minus, that will be your DSB, sorry, SSB signal. Okay. So that's the easiest way we have understood. So basically the modulator has been just defined by knowing that mathematical understanding. So you wanted to generate that, you immediately understood that, okay, it's nothing but this. So I need to do this MHT. So you devise a Hilbert transform circuit. Once you have that, it's just nothing but two modulator, one Hilbert transform, right. You can even tell that this is just the DSB-SC modulator. Multiplication is nothing but DSB-SC modulator. So basically this two are DSB-SC modulator, and you only have one pi by 2 phase shifter, which is the Hilbert transformer, and rest of the things another adder is required, that is all. But we have already talked about that this particular thing, that pi by 2 phase shift for each frequency, that is a very hard circuit to realize. Can we get some other circuitry which can do this? So I'll just give the practical circuitry that was proposed by Weber, that particular circuitry. So the practical circuitry is, it looks like this. So you have MT. So this is one arm where you have a multiplier. You multiply this by cos omega 0 t or 2 pi f 0 t. We'll talk about this omega 0, that's a, or 2 pi f 0. What is that? We'll talk about that. And this one in the other arm, you multiply by sin omega 0 t. Okay. After that, you put a low pass filter. I'll also talk about the bandwidth of the low means cutoff frequency of that low pass filter. Once you have done that, then you multiply with actual carrier. So this is cos omega ct, and this is where you multiply with sin omega ct, and you subtract them. What I am saying, I will be getting SSB signal as long as I tune this frequency properly and I put this omega 0 properly. See, the technique we are applying, that has a big historical significance, and that is why probably SSB you can generate for voice, but you cannot generate for video signal. We will talk about that. Where you can generate SSB signal, it is like this. Suppose I have a message signal which has no DC part or close to DC component. Okay, I have a typical message signal like that. So let us say it looks like this. Generally voice looks like this. Voice has a minimum frequency. So, less than 300 hertz there is nothing, okay, that will not significantly affect my voice signal. Okay. So, it has a minimum frequency, let us call that as FA, and it has a higher frequency FB, beyond which I do not need that. So, for voice typically it is 3.4 kilohertz, right. So, 300 to 3.4. So, FA is 300, FB is 3.4 kilohertz. If the signal looks like this, what I can do, the basic functionality of this is something like this, that I will take this signal to a small intermediate frequency, okay. And after taking it to small intermediate frequency, probably I will put my filtering. So, it is something like this. Why I am doing this? Because I have to somehow employ a filtering technique to create SSB. What I can do is something like this, that I modulate it first. Let us say I get a modulation something like this, and then I employ a low pass filter which has a cutoff frequency exactly at this and a roll off like this. Then it will reject this, it will reject this, or I employ a high pass filter which has a transfer frequency transfer function like this. Then it will reject this part and I will get this, very nice. For suppose a signal even like this, I can do that. I do a modulation, so it takes it over there, and then I put a ideal high pass filter. Now, this is where the problem comes. Do you have something called ideal high pass filter and ideal low pass filter which has a sharp cutoff? You will never find that. Always any practical filter which are stabilizable will have a roll off, right. And as you go to higher frequency, the amount of frequency it will take for roll off will become higher and higher, right. So, what is happening? It will have a roll off. Once it has a roll off, it is actually disturbing the SSB signal. So, I cannot allow that. So, basically I need to have a signal where I can still run this roll off. So, I was talking about this free zone. If I have that free zone, probably I will be able to allow this roll off. This roll off of the filter, I can allow this. And I also know that at a very higher frequency, I can do this, that I immediately modulate to omega c, whichever frequency I need, let us say 900 megahertz or something like that. And at that part, I only have a separation of 300 plus 300, 300 this side and 300 this side. So, 600 hertz. Within 600 hertz, if I wish to put my roll off, that will be very high order filter, and the corresponding filter transfer function will be almost non-stabilizable. They will not be able to, means you will not be able to realize this. Whereas what I can do is something like this, at a lower frequency I generate this filtering effect and then I translate it to a higher frequency. I can do that. This is what has been done over here. So, if you see now the circuit, it is pretty clear. You are doing at a lower frequency modulation, then you are employing the low pass filtering effect, so that the roll off is still realizable. After that, you are modulating with a carrier, right. That is all you are trying to do. So, that is the basic circuitry of Weber circuit, okay. But we will see he has done it in a little better way. So, we will try to employ that part. So, what he has done is something like this. Let us say this is the signal representation. This is my FA, this is my FB, this is minus FA and this is minus FB. So, the modulation he has employed is at a frequency, this F0 is nothing but FA plus FB divided by 2. It will be very clear why he has chosen this frequency. Okay. So, immediately if you do that, what will happen? If I do modulate with this frequency, so it will be translated by F0 on this side and F0 on the other side, right. There will be a translation F0 on this side and F0 on the other side. So, if I just give positive F0 translation, let us say it shifts at the positive frequency side, then what will happen? This f minus a plus f0 will be the frequency where it gets translated. So, minus fa plus f0 fa plus fb divided by 2, which is nothing but fb minus fa divided by 2, right. So, this frequency goes over here, this fa, and minus fb goes to minus fb plus fa plus fb by 2. So, that is actually fa minus fb divided by 2, or nothing but minus of fb minus fa, because fb is always greater than fa, right. So, it just gets centered at 0, and this will be your nu 2 frequency. Okay. The spectrum looks similar. So, only sorry, I have done it in a wrong way. So, this becomes fb minus fa by 2, this becomes fb minus fa by 2 minus of that, right. And the separation immediately you can see fb minus fa, which is the separation of this one. So, whenever I do give a translation, this part shifts to the middle, this part will go into 2f0, right. So, there will be one part centered around 2f0, and when I give negative shift, what will happen? Similar thing will be happening, this will be centered around this, and the other part will get shifted over here at centered around minus 2f0, right. Now, all I will be doing, the filter he has designed is actually, the filter cutoff frequency is this fb minus fa by 2. So, that means he is trying to take this portion. Okay. So, that is the only meaningful information he will be requiring. So, he is just taking this portion after the filter. Once he takes that, then he does rest of the things. Okay. So, this is what he is trying to employ. So, immediately we can see that f0 is designed as this, and the filter cutoff frequency is fb minus fa by 2, that what has been employed. So, immediately you know for voice what should be our overall thing, right. So, that is something we already know. Okay, fine. And remember, the big advantage is now it is no longer even a band pass filter, it is just a low pass filter that I will have to put. Okay. And that low pass filter is means it is the lowest frequency where you can roll off the low pass filter, because any other low pass filter, if you just modulate it to a higher frequency, the low pass filter will still go to some higher frequency, and then you have to put the roll off. You wish to put the roll off because the roll off region you have only 600 hertz for voice, right. You want to keep it as low as possible, so that the roll off can still be easily understandable or realizable. So, this is probably the best one you can do. Any other things you do, your filter overall cutoff frequency will be little higher, and the roll off of 600 hertz might not be sufficient. Okay. So, probably the Weber circuit is an intelligent design where this is the best you can do. You bring both the sideband overlapping in the middle, but because he has those two arms, you will see that he has manipulated it very well. After doing the subtraction, it will just generate with these two band, it will just generate the USB or LSB. Okay. So, we will see that part now. So, if I just go back to his circuit, that was his circuit. So, basically what we do, we take the MT in the upper arm, we multiply it with cos omega 0 t or 2 pi f 0 t, right. F0 value we already know now, fa plus fb by 2. So, MT or equivalent MF can be written as M plus F plus M minus F, that is the upper sideband and lower sideband, right. So, what is happening? If I represent this phi t as my MT into cos 2 pi f0 t just after the first multiplication in the upper arm, right. So, I can write this as MT into half e to the power j 2 pi f0 t plus e to the power minus j 2 pi f0 t, right. I can write it this way. Now, if I just do a Fourier transform, which is phi f t, sorry, f or phi f, right. So, if I just take a Fourier transform of this, so what that should be half, it is a Fourier transform of mt multiplied by this, mt is already this one multiplied by this gives a frequency translation, right. E to the power plus j will give a frequency translation of f minus, it will take it to minus f, right, f minus f0, right, and minus j 2 pi f0 will produce f plus f0, right. So, this will be, if I just write m plus f minus f0 plus m minus f minus f0, because that is the whole mf, right, mf multiplied by this, that will produce these two terms, and mf multiplied by this, that will produce another two terms which will be at plus f0. So, m plus f plus f0, m minus f plus f0, right. This is fine. So, we get this phi f, all right. Now, what we have employed? After phi f, we have put a filter. Okay. So, in the filter, which are the terms which will be vanished? So, this is the m plus 1. If you just go back to our filter representation. So, this is, so this gets translated to this side, that is actually multiplication by e to the power j 2 pi f0 t. Okay. So, there the negative 1 is getting survived. See, the negative half is, I give a translation, negative half is coming over here, positive half is going over there. This is the m plus part. Okay. So, I can write this m plus f minus f0, and this is actually m minus f minus f0, and this I can write as m plus f plus f0, this is on the other side, and this is actually m minus f plus f0, right. So, these two terms are getting rejected after the filtering. So, what I will be left with, if I represent that as phi f f, that should be half into, so two terms which are m minus f plus f0, that gets cancelled, and this other term which is this gets cancelled. Okay. So, we are left with m minus f minus f0 plus m plus f plus f0, right. So, you have understood this part. Similarly, we will have to do in the lower half also, we have to multiply by sign. Sign means it should be, whenever we do multiplication by sign, it will be 1 by 2 j, and here it should be this plus minus this, right, and we will have to do the translation. So, if I do for the with the sign, I will be getting, if I just write that as phi dash after filtering, it should be just 1 by 2 j, just do it yourself, it is algebraic manipulation, f plus f0 minus m minus f minus f0. So, we get this. Okay. So, now these two terms has to be multiplied with cos omega ct and sin omega ct. So, if I do cos omega ct multiplication, so immediately what do we get? So, suppose the upper arm I am trying to do. So, that is corresponding time domain signal, let us say phi f t, which is having a frequency domain representation, we have already done that, which is phi f f. So, this into cos omega ct, right, this is what we will have to do, which is nothing but, or I should say equal to phi f t into, again we can write half e to the power j 2 pi f c t plus e to the power minus j 2 pi f c t. Okay. So, if I just employ same thing, same technique of frequency translation, we will get again this half, and there is already one half. So, that should be 1 by 4, and I will get a term of m plus f plus f0 minus f c, this is one term, then I will get m minus f minus f0 minus f c, that is the another term. So, this is multiplication by Fc, and then minus Fc will give me another 2 terms, which is m plus f plus f0 plus Fc, and then I get m minus f minus f0 plus Fc. So, this 4 terms I get. Okay. After multiplication with cos, of course, the Fourier transform of that. Remember, it is not equal. We are doing the Fourier transform of that. In the Fourier transform, because it is multiplication by e to the power j 2 pi f0 t, it will be just translated at frequency minus Fc and minus Fc, both the terms. Okay, we had 2 terms, m plus and m minus, and same thing will be happening when we multiply by minus j 2 pi f0 t. So, it will translate it to plus f0. So, m plus that plus Fc plus Fc, right. So, it will have both the terms translated at plus Fc. So, this is what we get for the first term. In the second term, we have that phi f dash t already, that needs to be multiplied by sin omega c t. Again do the same thing. Okay, sin you can put as 1 by 2 j e to the power plus j 2 pi f c t minus e to the power minus j 2 pi f c t. So, if you just write that and again do a Fourier transform. So, what you will get is minus 1 by 4, and then the terms will be, if you just do that same translation. So, it should be m plus, we already had a component f plus f0, that will be translated at minus Fc, minus m minus f minus f0 minus Fc, and then another minus m plus f plus f0 plus Fc, and then you have m minus f minus f0 plus Fc, right. So, this is what we get. Okay. Now, all you have to do is subtract from this to this, right, because at the end after doing these 2 multiplication, you are just subtracting from this to this. Now, you will see some of the terms are getting cancelled, because this minus this minus minus will become plus. So, you are actually adding these 2. Okay. So, basically if you see this m minus f minus f0 minus Fc, that is plus. So, this term will be cancelled, and then this term will be cancelled. So, what you are left with is 2 this terms and 2 this term. So, 2 by 4 it will be, which is becoming 1 by 2, and you get m plus f plus f0 minus Fc, and you have another term which is m minus f minus f0 plus Fc. Very nicely this has created my DSB, sorry, SSB signal. If you just see what it is the m plus part, which is centered at frequency, or which is translated at frequency. If I just, because Fc is big, so or Fc is the greater one, so I can write it Fc minus f0, right. And this m minus has been translated to f plus Fc minus f0. So, the m minus part, okay, which is that lower part, has been centered at, m minus part, the m minus part is centered at this Fc plus f0, right. So, that should be m minus Fc plus f0. Okay. So, this is where it comes, this becomes the Fc plus f0, the center part. Okay. And this m plus part comes to this, again Fc minus f0, Fc minus f0, and this gets centered at, the m plus part centered at Fc minus f0. This is minus of that. Okay. So, you get a clear SSB representation, but you could see that we have never employed any Hilbert transform over here. It is just filtering, and that one filter that we have employed, where we can actually put roll off, provided there is that 600 Hz free zone. If there is no free zone, I cannot put that filter, because I will not be getting, even in low pass filter at a very low frequency domain also, I cannot get a sharp cutoff, right. That is not possible. There is no filter in this world which can have a sharp cutoff. So, due to that, only voice signal where you have that free frequency band at a lower or around DC, you can actually employ SSB. Whereas for video, which has the DC term and all the frequency bands in the lower frequency zone are occupied, you cannot really employ any SSB. So, SSB modulation is not possible for video signal, whereas SSB modulation for voice signal, that is possible. Okay. Whereas if you see, the voice band is pretty small, it is just 300 hertz to 3.4 kilohertz. So, there probably we will not be benefiting by reducing this, whereas in video band it is almost like 4.5 megahertz. If I just modulate it with DSB-SC, I will be getting almost 9 megahertz, but I know that SSB I will not be able to employ it over there, because it occupies the voice band, video band looks like this. So, no way I can put a filter like this. Whatever I do, I will never be able to employ this filtering, right. So, there is a big difficulty in this. So, I will never be able to work out that in video. So, can we get any other modulation that might not give me as efficient as SSB, but some efficiency where I can still have a filter roll off? That is where the modulation technique called vestigial sideband gets popular. Okay. And we have just seen the end of probably analog video transmission. So far it was analog video transmission, even in many places I think it is still analog video transmission. If it is analog video transmission, it is employed with vestigial sideband. Okay. So, the vestigial sideband will see that there is a filter roll off still we can employ, and it might not be as efficient as SSB. That means it just occupies half the frequency, but it will still be good enough. Okay. So, what we will do next is we will try to see what is this vestigial sideband modulation, okay, that we can employ for a video signal. After doing that, we will also try to see how do we demodulate DSB-SC signal as well as SSB-SC signal, because we still have to know this is all about modulation, right. We have not talked about demodulation. So, we will talk about demodulation of these signals later on. Okay. Thank you.